The first part of this problem is going to be a good review for Euler's method, one of the easiest types of problems that you can encounter in paper 3. This one says, consider the differential equation, and it gives me an equation, given that y equals 2 when x equals 0. Now, anytime they give you a point on a differential equation, please be aware that if you don't use it sometime during the problem, then you're doing something wrong. And this can be solving for a constant at the end or something like that. In our case, it's going to be an initial value that we start with. So this says, use Euler's method with a step length of 0.1 to find an approximation to the value of y when x equals 0.3. So I know something about when x is 0, y is 2. I need to get up to 0.3. It's telling me to go by steps of 0.1, so not too many steps. Now this, Euler's method, I have just copied this, okay? This is right here on your formula sheet under topic 9, okay? So I just copied this already to get us ready for what we're supposed to do. So basically you know that you're starting x equals 0, y equals 2, and you know something about the derivative. Well, you're going to need the derivative because in this, this does represent the derivative, although it doesn't state that it does on your formula sheet. Okay, and so we have the derivative here. We do need to solve for dy dx. So all we need to do is bring this over to the other side. So this would be cosine squared x minus y times the tangent of x. Okay. Now our x's are going to be easy. All you have to do is keep adding the step value to the previous x term. So your x values are just going to go 0.1. This is like your x naught and your y naught. And so this would be x1, x sub 2, going up by adding 0.1 again. X sub 3 would be 0.3. So that's no trouble. The question is what's happening to the y, and these are actually tangent line approximations. Okay, but we can go ahead and say it's going to be equal to the previous y value, which is 2, plus h is your step size, 0.1, times the derivative evaluated at the previous point. Okay, so I'm substituting into the derivative formula using the x and y from the previous point. So this would be cosine of 0 squared minus 2 times the tangent of 0, just substituting in 0 and 2 into this equation. Now notice I did change how I wrote it because you do have to enter it in the calculator that way. Okay, so I'm going to take a minute. I'm not going to put all of these in, but I do want to just remind you that you need to be in gradient mode for calculus. It looks like I'm in good shape here, and I'm just going to put in, now you can program a little spreadsheet to do this for you. You certainly don't have to. They're not going to ask you to do all that many steps. Okay, so I want the cosine of 0, and actually I want the cosine of 0 to be squared. Let's see, kind of overdone in my parentheses here. Let's say cosine of 0, and that's squared, good, minus 2 times the tangent of 0. And I think we've got enough parentheses. We'll just see how that goes. We've got a nice little 2.1. That shouldn't be all that shocking to us because the tangent of 0 is 0. So that goes away. Cosine of 0 is 1, so it's just 2 plus 0.1 times 1. Okay, so clearly we could have done that in our head, but at least I have shown you once how to make sure you can substitute that in on your calculator. So this is our y1, and now we know our y1 is 2.1. Okay. So if you just kind of want to pair it up there, x1 is 0.1, y1 is 0.2. Going on to the next term, we would figure out our y2. Using the formula, you're going to use your previous y value plus h, which is 0.1, times the derivative evaluated at the previous point. So again, we're using this formula, but you're substituting in 0.1 and 2.1. So this would be cosine of 0.1, and that would be squared, minus y times the tangent of 0.1. So clearly, we're not going to be able to do those values in our head. So you're going to put all those in on the calculator. And when you do, I got 2.17793. Now, you don't want to round until the end. So try to keep a significant amount of digits until you get to the final step. Okay, so we have x2 and y2 now. For x3, we'll find y3, which again is just y at the previous point, plus your step value times the derivative evaluated at this point. Okay, so this would be cosine of 0.2, that quantity squared, minus y. And if you don't feel like writing that out, you could just put y2, something like that, so they know what you're doing, and then times the tangent of 0.2. Okay, so when you put all that in on your calculator, you get 2.22984. So when it says find an approximation for the value of y at x is 0.3, we have that it's approximately 2.22984. Okay, and again, you can round that to 3 places if you would like to. Okay. Alright, the next part is asking us to actually solve the equation. Okay, and so when we look at this, it says show that the integrating factor for solving the differential equation is secant x. So they're trying to make sure that you have an entryway into this problem. Okay, and so we have from before, this is what they already gave us, and they already gave us the point. Okay, this is actually from your formula sheet. Okay, so I've already written it on here, but it tells you if you're trying to find an integrating factor for something of this form, it's just e to the integral of p of x dx. So again, we're going to have to make sure it's in this form first. One thing to notice is that y is only to the 1. So if you have something that's y squared or higher, then that would tell you, hey, this isn't an integrating factor problem. They don't always lead you to which type of differential equation that it is. Okay, but we could have figured that out by this y. Okay, so I just kind of prefer, I'm going to make sure this lines up. This would be my y prime. Okay, I just have a y, so tangent x is clearly p of x, and here's my q of x. Okay, and so the only thing I kind of have to watch for sometimes if they have a minus here, then I have to remember that p of x is actually like negative tan x or something like that. We don't have that problem in this situation. Okay, so for me, if this is the integrating factor, I just need to do e to the integral of tangent x dx. Okay. So this would just, and this is your integrating factor, this would be e, and tangent isn't one of the ones we know, so I'm going to change it to sine over cosine. And in this case, your u would be cosine x. Your du would be negative sine x. So I need a negative 1. And to compensate, I'll multiply by negative 1 on the outside. So the net change is nothing. I multiplied by 1. Okay, and so then this is just e, and then this is the integral of du over u. Okay, so all of this dx there is actually your du, that's your u. And so this would just be e to the negative ln of the absolute value of u. You can just, in this particular case, we're going to go ahead and just say ln of u. And so we're going to have u, which is cosine x. And then we'd like to just cancel. You know, we'd like to know these are inverses, e and ln, but we need to move this negative 1 up here first. So this would be e to the ln of cosine x to the negative 1. Okay, so not just the x, but the whole term there. Now these are inverses and undo each other. So you get cosine of x to the negative 1, which is secant x, which is what they asked us to show. Okay, so we got the first part. Then it says, hence, solve the differential equation, giving your answer in the form y equals f of x. So they're just saying, when you get done, solve it for y. You could lose a mark or something there at the end if you don't do that, but it's not going to be catastrophic. Okay, so we've already got it in this form, so I'm just going to write that over again. So we're going to do y prime, I'm just going to write it as y prime instead of dy dx, plus y times tangent x equals cosine squared x. Okay. Now the idea here is you multiply both sides by the integrating factor and integrate. Okay, so I'm just going to write that down just to remind you. Multiply both sides by the integrating factor and integrate. Okay, so what you're doing is you're multiplying this side by secant x, you're multiplying this side by secant x, and you're integrating. Okay? Now, what you want to remember here is we've already proven this, but when you integrate this side, it's just going to come out to be y times whatever your integrating factor is. Okay? We proved that. We know what happens every time. We proved it for the general case. Save yourself a lot of time. Y times the integrating factor. Okay, but this side you're going to have to actually integrate. Okay, so just looking at how we can do that, it seems reasonable to change this to 1 over cosine. So we have cosine squared x times 1 over cosine x dx. One of your cosines cancels, okay? So one of these guys, so you're really just integrating cosine x. Now that's easy, it's a rule on our formula sheet, and the only thing is everybody gets confused when they're going back and forth between taking the derivative and doing the integral. If you forget, let's not lose any marks on this, okay? Let's just kind of go over here and make sure we're going to get it right, okay? The integral of cosine x is sine x. Okay, so everybody just forgets when is it negative, when is it positive. That'll just make sure you're right. Okay, and now they said to solve it for y. Okay, so two things: solving it for y and the fact that we have a constant to solve for it. They didn't say solve for it, but they gave you a point. And if they give you a point, they expect you to substitute it in, and that's a fair amount of marks for doing that, and it's really simple. Okay, so what I'm going to do is I'm going to divide through by secant x, so it's by itself. Now you have to understand that you're also dividing the constant by secant x. You can't just say a constant divided by secant x is still a constant. You cannot do that. Okay, you could substitute in your point before you ever do the division. Either order is fine, but please remember when you solve for y, you are dividing both terms, including the constant, by the secant x. Okay, so now we have y equals sine of x plus c over secant of x, and we have the point x equals 0, y equals 2, so we're just going to substitute that in. So 2 for the y, sine of 0 plus a constant over the secant of 0. Well, secant is just the reciprocal of cosine, so we know the cosine of 0 is 1. Take the reciprocal of that, it's still 1, so this guy is 1. So you'd have 2 equals sine of 0 is 0 plus c over 1. So altogether you just have that the constant is 2. Okay, so then just substitute that back in. Sine of x plus 2 over the secant of x. And that is a perfectly fine way to leave that. If you want to separate it out into two different parts, you can, but I'm just going to leave it like